Hi, this is Andrew James Hurleman, Skylar Cook, and Abner Ayala, and we are presenting on lung cancer detection from CT scans with deep neural networks. Just to give an introduction on what we're doing here, we participated in the Kaggle 2017 Data Science Bowl, which consisted of classifying CT scans of the lungs as cancerous or non-cancerous. The motivation for this is that lung cancer has a high mortality rate and is the leading cause of death for cancer-related illnesses. Early detection can help this, and we figured automated detection via machine learning may make this approach more feasible when applied to screenings. So there is some current work being done in the medical industry. It is being used to classify liver tissue, skin cancer, as well as lung cancer. The best results typically come from convolutional neural networks. They show the best results in image classification problems. And transfer learning is also being used in this field. It's the process of taking the learned weights and feature representation of one trained model and then using them as input into another. So a little bit about the data that we were given for this competition. It came in DICOM format, which is a typical radiology format. So CT scans typically come as that format. There were a variable number of slides per scan, which depended upon the equipment that was used and the thorax size of each patient. They came in grayscale images, which is dissimilar to what you would typically see in a 3-channel RGB image. And that matched up with the fact that these were in Hounsfield units, which is just radio intensity. We also used, as mentioned before, the transfer learning. We used a model which was pre-trained on ImageNet dataset, which is a large data set with 1,000 classes. The technology that we used was Python as the main language. We did a bunch of data exploration with Jupyter, and for the deep learning framework, we used Keras, which is a layer built on top of TensorFlow. For the pre-processing, we took the DICOM images and converted them into NumPy arrays. We clipped and normalized the images to narrow the search space, and we sliced the triplets to group them as mock RGB images so that they would work on the pre-trained ImageNet weights. We only used the middle scans to reduce the search space again and deal with the variable number of slides, as we figured that the cancer would typically be relegated to the center part of the lungs. So we asked ourselves in the beginning, how do we classify 3D images? In general, it's still a hard problem. The state-of-the-art uses voxel-based approaches, but this is still an extremely computationally expensive, convolving in 3 dimensions, and a very young approach with little library support. So we tried to turn them into videos, but it didn't really work out, and we had to pivot to a new approach. So the new model was an exception architecture, which was originally proposed by Francois Collet, and we attached 2 fully connected 1,000 node layers on the end of the exception to create our feature vectors. The feature vectors, which were output by that, were fed into a random forest to give us our labels. You can see that model here. Here are the images, moves over to the exception model, and then this spits out the feature vector fed into the random forest, and then we're given our labels over here, which is the results. Here are our results. They're, as you can see, a little bit tepid. Some numbers that stand out: the true positive rate, 62.65%, and false negative rate, 37.34%. Not the best, but that leads us to our conclusion. that transfer learning with ImageNet is, for this field, just simply not feasible. They're dissimilar, and we spent a lot of time trying to coerce the input data into a format that, for the transfer learning, which may have made us struggle a bit. The input data was not sufficient to achieve great results. The best results came from using external data sets, such as the Luna 16, which invariably in the top competitors on the Kaggle competition ended up using that. So although the results were suboptimal, there's hope for improved results in the future. Again, one of the things that this suffered from was really the limited data that the competition provided. And I really think that better results will come with improved data sets and obviously fine-tuning of hyperparameters and architecture. That is all, and thank you for your time.